Hello class, and welcome to another beautiful day in physics land. Today what we're going to be learning about is something called angular momentum. Now, we have already talked about linear momentum. You heard some lectures from me and from Khan Academy. Angular momentum, as we will find, is pretty much the exact same thing, which means any problem you can do with linear momentum, you can also do with angular momentum, with some complications. So first on our list, we're going to go over the differences between linear and angular motion again. Then we're going to talk about something called the moment of inertia. And then we're going to finish up with some example problems. Now I'm going to try something funny here. I'm going to play you a YouTube video through this YouTube video. Ooh. I have no idea how well that's going to work, so I will also link the video regardless. Alright, linear motion. Let's go ahead and get started. This notes you will want to be writing stuff down. Linear motion, things that we care about in terms of linear motion. This covers everything we've talked about so far this year. Time. How far something has moved. How fast something has moved. The rate of change of its how fast it's moving. Its resistance to a change in motion. How hard you gotta push it to enact some sort of motion. And how much it wants to keep moving. Now, also on this list, of course, is energy. I took it off the list because energy is pretty much the same regardless of it being linear or angular. And we're not going to be doing any angular energy, so don't worry about it. Now, time. Okay, that's easy enough. Measured in seconds. How far something has moved. Well, that sounds a lot like displacement, measured in meters. How fast something has moved. Measured in meters per second. So a time is just how many seconds. Delta x, the change in position, how far it has moved, measured in meters. And v, velocity, how far it has moved, divided by how much time it took for that movement to happen, gives us our velocity. Now, the rate of change of velocity, that, of course, is acceleration. Now, resistance to the change in motion, that sounds a lot like inertia, or mass, which we measure in kilograms. Alright, now, how hard you're pushing something to enact some sort of change in motion, that's a force. Measured in newtons. And how much it wants to keep moving, again, that sort of sounds like inertia, or momentum. And this is measured in Newton seconds, or, if you prefer, kilogram meters per second. Either of those two are equivalent. Alright, now the only really interesting thing about linear motion is what delta x is, so I'm going to draw a little picture. That's where you're here, and you end up over there. Delta x. Crazy. Alright, now, angular motion. So instead of talking about moving in a straight line, now we're talking about moving in some sort of circular motion. Time is unaffected by this. We still measure time the exact same way. Now, how far something has rotated, we measure that with an angle. But we can also use an angle to just represent a position. So I'm going to slap that on there to remind us, more than anything, that what we're talking about is not where you are on a circle, but the movement from one position on the circle to another position on the circle. Now, we can measure this in degrees, or we could measure this in radians. If we want to measure in radians, that would give us s equals theta times r, where r is the radius of the circle, and s is the arc length of the displacement. Or, if we are dealing with degrees, which I would very much prefer, that's theta times pi over 180 r. All right, cool. Now, how fast it is rotating. That's not a W, although it looks like a W. That is Greek letter lowercase omega, and it represents angular velocity. All right, so angular velocity, what is that measured in? Well, that would be in radians per second, or, preferably for us, if we're doing degrees, that would be degrees per second. Although it could just as easily be radians per second. Now, of course, radians, you don't actually write radians, so we should just write this per second. Whatever. All right, the rate of change of angular velocity gives us angular acceleration. Ooh. Notice I stopped writing the equations. I could write them. I'll write them. And delta omega over delta t. All right. Now, resistance to the change in rotation. Things like to move. We call that inertia. Things like to rotate. That's also called inertia. When something is moving, be it linearly or angularly, it wants to keep doing whatever it's doing. How much it doesn't want to change what it's doing is measured either as mass or as the moment of inertia. More on this in a moment. Now, how hard you're pushing something causing rotation, that's torque. And how much it wants to keep rotating, well, that sounds like momentum, except angularly. All right, equation time. Torque has a few ways that we could look at it. So, we have the F times R thing. You can also look at it as, and I gave you this equation before and I said don't worry about it, moment of inertia times angular acceleration. Notice that it looks a lot like F equals m times a. It's just another application of Newton's second law. Now, the big one we care about for today is L. Angular momentum. It's equal to the moment of inertia times the angular velocity. Ooh, fancy. Now, additional thing I'm just going to add here on the bottom, please remember that we have this thing called impulse. Force times change in time, and that gives us the change in momentum. That is still true for angularness. How hard you push it multiplied by for how long you're pushing still gives us the change in momentum. All right, so, sorry about that. I had to pause for a moment. All right, so, linear motion as opposed to angular motion. It's exactly the same, with the differences of instead of from point A to point B in a straight line, we're going from angular point A to angular point B, rotating around some center axes of rotation. Yay, fun stuff. So, the big question that you're probably asking yourself is, Mr. Salzo, what the heck is the moment of inertia? Well, you can think of it like mass, but it's more than that. The equation is that. The integral of r squared over dm, or dm, equals I, the moment of inertia. what does that tell you? Okay, so for those of you in calculus, you know that this is sort of kind of like summation. It's saying if you take up all of the mass in an object and multiply it by the distance between that bit of mass and the axis of rotation squared, you get a number. And you do that for every single atom, and add all those things up, that would give you the moment of inertia. Now, luckily, some people have already done all this for us. So we have a huge table of moments of inertia that you just gotta look up and plug in numbers for. More on that in a moment. What we care about is a wordy definition. This is how the mass is distributed in an object. It's not just how much mass it has, but where that mass is. Because it turns out that the most important thing for causing something to rotate is not just how heavy it is, but the distance from the axis of rotation. Axis of rotation. Which means that if, I got an axis of rotation here, and I got that, and it's, making some path like that, the total mass of whatever this is isn't that important. It's important, but it's not nearly as important as the distance between it and its axis of rotation. So, for our moon, that would be the axis of rotation is around the Earth. So you would take the mass of the moon, roughly, and multiply it by the distance from the moon and its axis of rotation, squared. Alright, takeaway. What do we care? The more the mass is spread out, the harder it is to rotate. Which means a bigger moment of inertia. We know this. Here's a good example. If you pick up the desk, so here's your desk, and here's you. Go ahead. Pick up a desk, and then rotate with it. 180 degrees. Alright, I'll put it back down. Alright, that was not horribly difficult. Now, pick up the desk again, and extend your arms out all the way. And now rotate it 180 degrees. Harder. Harder because, one, your arms are working harder, but also harder because the mass is further away from its axis of rotation. It is not just that your arms aren't strong enough because of leverage, it is also that moving something further away from you is just plain harder. Alright, desks back where they go, blah blah blah, you're all looking at the screen again, notes and pencils and so on. Two side notes before we move on. The period. We've talked about the period before, represented by capital T. It is the time of one rotation. Which means the linear velocity, which is delta x over delta t. If you're rotating, one complete rotation is a circumference. The time it takes to make one complete circumference is the period. Alright, that's cool and important and stuff. Let's see, remember, of course, that this is 2 pi r. The period can also be given by the angular displacement times the angular speed, which is really just this equation rearranged a little bit. You'll notice that. All right, that's cool. Another thing, what do I mean by rotation? What I mean by rotation is going in some sort of circular motion or part of a circular motion, where this type of rotation is different from this type of rotation. But it's more complicated than that. Or those are my axes of rotations. This is not just counterclockwise. This is not just clockwise. There is also what plane it is in. So, okay, look at the computer screen. It's straight up and down. This is rotating clockwise in a plane that is straight up and down. Where this is rotating clockwise in some plane that isn't straight up and down, where my dotted line represents my axis of rotation. What this means for us. When something is rotating, it wants to keep rotating the exact same way. Which means not just that if something's rotating in the clockwise direction, it's going to keep rotating in the clockwise direction forever and ever and ever, but it's going to keep rotating within the same plane as well. And this is what keeps tops, dreidels, and gyroscopes up. So, here's my dreidel, and it's spinning like this. It will not fall over until it stops spinning, because as long as it is spinning, it has angular momentum, and angular momentum is conserved. So it wants to keep angular momentuming the way it is, which means it has to keep rotating like this. This is a different kind of rotation, even though it's the same dreidel, still rotating in the same way, since it is no longer rotating within the same plane, different type of rotation, different angular momentum. So, this doesn't happen. Your dreidel just keeps spinning like this, forever and ever and ever and ever and ever, or until it slows down because of friction. Alright, now, here's a table of common moments of inertia. If you have a thin rod that rotates about its center, so the axis of rotation is represented by the red line, where this is R, then I equals 1/12 total mass of the rod times R squared. If you have a thin rod rotating about its edge, so this would be you twirling a baton in your hands. This would be you having a meter stick and swinging it back and forth, swinging a sword, a baseball bat, something like that. I is going to be 1/3 m r squared, where this is r. So even if it's the exact same thin rod, its moment of inertia is different depending on what it's rotating around. Now, a slab rotating around its dead center, that's going to be I equals 1/12 m a squared, where this length here is a. This is going to be 1/3 ma squared, where this length is a, as in a, b, c. A cylinder or a flat disk rotating about its center. this is just mr squared. Some point mass, like the moon, rotating around some center axes, like where Earth is. Notice that this and this have the same moment of inertia equation. A hula hoop has the same moment of inertia as a rock on a stick, or on a string that you're swinging around. A cylindrical hoop about its center, so okay, this would be the better example of the hula hoop. This is... Sorry, just checking the notes. Oh, look at that. Fancy, fancy. Alright, now a solid sphere, so this is like a ball bearing or something, about its center, or I should say about its diameter. That's 2/5 mr squared. A hollow sphere, like a soccer ball, now, this entire table came out of your book. Page 216. If I were you, I would take a look at it as well in its pictures, just in case my pictures didn't make sense to you or I did something wrong. I'm 90% sure I didn't do anything wrong, but it can't hurt to check. Just my feelings. Moving on. We're almost done. There are two examples that we are going to talk about. The first example is an ice skater that is spinning. The moment of inertia depends on not just the total mass, but how it's distributed. So, here we have an example of the mass that's all bunched up close to your axis. Here we have an example of a spinning ice skater where the mass is far from the axis. Alright. This means you have a nice small moment of inertia, and this means you have a nice big moment of inertia. Which means, if you start spinning like this, and then you stick your arms out, you have changed your moment of inertia in the middle of a spin. Well, conservation of angular momentum states that your angular momentum is conserved. Which means, where here you have a nice big angular velocity, here you get a nice small angular velocity. Which means, when you start spinning, you bring your arms in and legs in nice and close, and you spin nice and fast. You spread out again, and you slow down. Fast, slow, fast, slow, fast, slow. You can do this on any sort of rotating chair or stool. If you ask the sub real nicely, they may lend you my chair from the front of the class. Make a nice clean area, and spin around as fast as you can with your legs tucked in, and then shoot your legs out. And you will slow down. Now, bring your legs back in, and you will speed up again. Ooh. Alright, so here's the picture, or the video, I should say. We'll see how this works. YouTubing a YouTube video. So, here's an ice skater. She starts to spin with her arms and legs out. Angular momentum is conserved, so as she brings her body closer in, she speeds up. And then she brings everything back out again and slows down. Awesome. Last example. Merry-go-round. So you got a big thing, you know, it has the little handles on it or whatever, right? Kids jump on it, and they have a lot of fun having it spin around and around and around until they puke. I always did. Little Joey is standing right in the dead center, right on its axis of rotation. Joey has a mass of 36 kilograms. The big merry-go-round thing has a mass of 200 kilograms. It is rotating such that it has a period of 2.5 seconds. Alright, well, at least initially it does. While it is rotating, which means angular momentum must be conserved, he walks to the outside edge. Now, my merry-go-round has a 2-meter radius, so he's now 2 meters away from the center of the axis. What's the rotational period of the merry-go-round? Alright, well, let's see. Initially, he has a period of 2.5 seconds. In a moment, I'm going to ask you to pause and do it on your own, and then hit play again when you're ready to see the answer. For right now, though, let's set it up together. So, it has some initial period. We know that the mass of Joey is 36 kilograms. We know that the mass of the merry-go-round is 200 kilograms. We know that the radius, or I should say distance, between the axis and Joey is 0 meters. And the distance between the outside edge of my disc, or merry-go-round, and the center is 2 meters. So it looks like there's going to be 2 moments of inertia. I'm going to find the moment of inertia for Joey, and I'm going to add it to the moment of inertia of the merry-go-round, and that will give me the total moment of inertia. Alright, one thing before I let you guys go. If you know the period, you can find me the angular velocity. If you can find me the angular velocity, you can find me the angular momentum. Of course, you know. First you gotta find me the total moment of inertia. Then, angular momentum has to be conserved. You can find the moment of inertia there, so you can find the final angular velocity, which should let you figure out the final period. Alright. Please now pause, do the problem, and resume when you have an answer. Go! Alright, so, you're done. Okay, let's see what we got. Well, let's see. Point mass, that says I equals mr squared. And disk, ooh, disk. Cylindrical disk thing rotating about its center, that's 1/2 mr squared. Alright, so I equals mr squared, where r for Joey is 0, so there is no moment of inertia because of Joey. I don't care. But there is a moment of inertia because of the disk. So the disk is going to be 200 times 2 squared, which gives me 4, divided by 2. So I'm just going to say 200 times 2, which gives me 400. 400 what? Okay, well, let me look. 1/2 kilograms and meter squared. So this would be kilogram meter squared. All right. Okay, so let's see. I need my angular velocity now. Oh, how am I going to do that? Well, I know that one complete rotation is 360 degrees, and he does 360 degrees in 2.5 seconds. So 360 degrees in 2.5 seconds. That gives me, math time go, 144 degrees per second, which gives me a angular momentum of 57600. 57600 watts. Ooh, that would be kilogram meters squared degrees per second. Wow, that's ugly. Alright, so, but in any case, there we go. New moment of inertia, well, it's still going to be 400, except now it's going to be 400 plus an additional, let's see, 36 times 2 squared. 2 squared is 4, so 36 times 4, which is 144. It gives me 544. Okay. Well, I have my moment of inertia, and I have my angular momentum, so I can solve for my new angular velocity, which is going to be that big ugly number divided by 544, which is going to give me 105.882 degrees per second. That's too many sig figs. I should have just made it 109, or sorry, 105.9, whatever. Now to find this. Ooh. Let me think about that. Well, I know that it does 105.9-ish degrees every second, and I want it to go 360 degrees. So, oh, wait a second, Mr. Seisel gave me an equation. This is its speed, and I want it to go 360 degrees. That will give me the period. So I'm just going to multiply this number by 360. That makes sense? Wait. No, nope, it doesn't. Angular momentum is going to be that over that. So P is going to be... I caught a mistake. So, alright, make sure that this is written correctly earlier in your notes. I did it wrong earlier. Alright, so it's going to be 360 divided by that. That makes much more sense. Much more sense. Alright. 3.4 seconds. Done. Didn't like my explanation? That's okay. This is straight out of your book. This is the example on page 276. Alright. All done. Good job, guys. Good game. Good game.